interested in. Maybe we're interested in 7 years growth. Fine. Measure the radial increment over the last 7 years. Right? And we need to double that to get increment, to get DVH increment. And so our best estimate of past DVH inside bark would be the difference between those two. But of course, when we talk about DVH, and when we're measuring trees on a plot, we don't measure DVH inside bark, we measure DVH outside bark, right? If it's not specified otherwise, we always assume that when someone says DVH, they mean outside bark. So there also is going to have to be some assumption about bark thickness when we do that calculation. Of course, we can observe bark thickness right now, right? You can see it on your core, as you will see in the next slide. But does that mean that that's how thick the bark was 10 years ago? No. So we need to have some assumption about how bark thickness, maybe it's a constant proportion of DVH. Right? We can make an assumption and come up with a way to convert that past inside bark increment to outside bark increment. Then we can apply this directly observed growth information, either by DVH class, right? Because we want a range of sizes that we're going to core trees for. So we can apply those numbers, take averages by DVH class and by species, and apply those directly. Or we can smooth those results with a regression equation. And that latter is really going to be the preferable way to do it.
Question? So you're applying past growth.
We're calculating past. Last 5 years growth, last 7 years growth, last 10 years growth.
So that's what you're applying.
That's what we calculated.
Okay.
Yeah. So we have to do a little bit of fiddling around with this increment core data. Take some measurements, fiddle around with it a bit to get what we're actually interested in. So this one's blown up a little bit better, and it's a red pine, so we can very clearly see the annual rings, right? So if we're interested in 5-year increment, well, we can see the bark thickness, right? We can measure bark thickness, and we can count back the number of years that we're interested in increment for, measure that radial increase, and then double it to get deviate, to get diameter increase. Here's an example of someone who did a stand table projection, collected those data like I'm describing, and then fit regressions to the data. So on this axis, they have 10-year diameter growth. That would be the last 10 years, right? Diameter growth over the last 10 years versus DVH 10 years ago, right? Not DVH now, but what the DVH of the tree was 10 years ago and how much increment occurred on that DVH of tree over the next 10 years. And you can see they did it by different species cohorts, and so forth. So once we have these equations, we can use the equation to predict DVH growth based solely on DVH. And of course, these growth and yield models that we're going to be talking about extend the number of factors that we will consider for predicting future growth. Well, that gives us, we got the stand table now, and we got a way to increase diameters in that stand table. But there are these other two components, stand-in growth and mortality, by DVH class. Well, you might say, well, no mortality is no problem. When I'm out cruising my stand, I'll just take a look and see, well, how many trees died on this plot? Well, maybe you can see dead trees, but do you know when they died? No. Right? Particularly once they start falling to the ground and decaying and so forth. So direct observation of mortality, really difficult, unless, of course, we are constantly monitoring things. But we need that information because that's a component of growth. So we can't calculate net growth, for example, if we don't have estimates of mortality. Same with stand-in growth. Now I say here, notice I say not just in growth, but I say stand-in growth. In growth we define to be trees reaching a size that we're interested in, right? So maybe we're only interested in trees 6 inches and larger. In growth would be movement of trees into that 6-inch class, right? Stand-in growth is in growth of new trees. So regeneration is what I'm talking about, or maybe trees growing into the 1-inch class or the 2-inch class. Not in growth, meaning growth of trees into a merchantable size. These are the two weak links in stand-tail projection. We have real difficulty observing these in a particular stand. And we'll see what the implications of that are in terms of the ideal type of stands that we apply this technique to. Okay, so let's look at the approach and do an example. First question on the homework, stand-tail projection. And I think it says in the homework, I'll say it right now if it doesn't. The first question on the final exam, the last exam, will be stand-tail projection. That won't be the first question. It'll be like the third or fourth question. Okay, so we're not actually going to grow trees. We're going to grow DBH classes. And we're going to move trees between DBH classes. We're going to observe their movement between DBH classes. What trees are we going to move between DBH classes? Surviving trees, right? The dead ones don't move, or the cut ones don't move. So DBH class movement of surviving trees. To do that, we're going to make two assumptions, and they're actually variations of stand-tail projection that make different assumptions. These two make the most sense to me. We'll first assume that the trees within a DBH class are uniformly distributed. That does not mean we have a uniform DBH distribution. It says each class is uniformly distributed. So if we have 1-inch diameter classes, the 1-inch diameter class would go from 4.5 to 5.5. It says we have an equal number of trees across that whole class. The number of trees in the 6-inch class will be different. So trees within a DBH class are uniformly distributed, and all trees in a class grow at the same rate as the midpoint tree. So again, if we're looking at the 5-inch class, going from 4.5 to 5.5 inches, we'll assume all those trees grow at the rate of a 5.0-inch tree. Okay? So, how do we go about moving trees between classes with those two assumptions? Well, let's look at a couple of examples. Here's a 2-inch DBH class where we have 1-inch widths. So the 2-inch class goes from 1.5 to 2.5, right? 1 inch wide. Let's say we assume that 2-inch trees, which means all those trees, right? Because they're all growing at the rate of a 2-inch tree. Let's say 2-inch trees are predicted to grow 0.8 of an inch in 10 years. So the 1.5-inch trees will become 2.3-inch trees, the 2-inch trees will become 2.8-inch trees, and so forth. So here's what that class looks like before we grow. Here's what it looks like after we grow. And of course, we're only considering the surviving trees, right? So the same trees are present at both points in time.
And you're determining that increment growth by the midpoint in the DBH class at 2.
We're assuming that all the trees grow at the rate of the midpoint tree.
2.0 tree, okay.
Okay? So now we need to, once we've grown the trees in that 2-inch class into a future distribution of trees, we need to observe what percentage of trees grew to the 3-inch class and what percentage of trees, therefore, stayed in the 2-inch class. Well, the break point is at 2.5 inches, right? Anything less than 2.5 is still in the 2-inch class. Anything greater than 2.5 is in the 3-inch class. So you can see here that 80% of the trees moved one class. 20% of the trees stayed put. Right? 2.3 to 2.5 is 20% of that width. Second example. 2-inch class again, but now 2-inch width classes. That's the difference between the left-hand side and the right-hand side. So with 2-inch classes, the 2-inch DBH class goes from 1 inch to 3 inches, right? That's 2 inches of width. And let's say we assume this time that 2-inch trees are going to grow 1.4 inches in 10 years. So 1-inch trees will become 2.4-inch trees, 2-inch trees will become 3.4, 3-inch trees 4.4. Right? Just add 1.4 to every initial diameter. Again, we have to ask the question, well, how many trees grew from the 2-inch class to the next class? Of course, the next class is the 4-inch class, right? Because we have 2-inch widths. And the break point between the 2-inch class and the 4-inch class is at 3 inches. So what percentage of trees moved over those 10 years? What percentage of trees moved over those 10 years from the 2-inch class to the 4-inch class? 70%. 70%. And the remaining 30% stayed in the 2-inch class. So maybe we can develop a rule based on those two examples. Do some deductive reasoning, inductive reasoning, I guess. To do that, we'll define a quantity we call movement ratio. The book uses the letter G, small g for this. I guess they call it growth increment or growth ratio or something. To me, it's really a movement ratio, so I'm going to use M, movement ratio M. And I define that to be the ratio of two quantities. DBH class increment, so in the first case, 0.8, in the second case, 1.4, divided by class width. In the first case, we're using 1-inch width classes, so class width is 1. In the second example, we use 2-inch width classes, so class width is 2. So what's the movement ratio in the example on the left? 80%. 80%. 0.8. Right? 0.8 divided by 1, 80%. What is it for the example on the right? 70%, 0.7. Remember how that 0.8 and that 0.7 factored into our determination of how trees move classes? With that movement ratios, we can identify two cases. And you might ask, well, aren't there more than two? Well, yeah, there could be more than two, but these are the two that will most often occur. And you can figure out what the third one is, or the fourth one, once you see these two. If that movement ratio is between 0 and 1, we interpret that as saying M, expressed as a percentage, is the percent of trees that move one class.